Designing the cantilever wall of a RC barrier for bending. This lecture deals with the bending of the stem wall. The effective length of the wall, which resists the impact, may be assumed to be equal to twice the height of the wall. The effective stiffness of the equivalent non-mesh system, as shown on the lower part of the diagram, is based on matching deflections when a quasi-static load of equal magnitude is applied to both systems. The amount of lump mass representing the wall may be taken to be equal to 1/4 of the total mass of the wall. Recall the earlier lecture on the fundamentals, the velocity of the target, and the amount of string energy by the supporting pole has been determined. This same expression may also be used for estimating the amount of string energy absorbed by the stem wall in bending. In this example of a wall which is impacted by a boulder weighing 200 kg at impact velocity of 5 meters per second, the value of lambda m is first determined, then the effective cross-sectional area taking account of cracking in concrete, and this is a simple assumed expression. Then the effective stiffness of the wall is hence found. Given the value of lambda m and the effective stiffness of the wall, the amount of deflections of the wall generated by the impact of the boulder can be found by the use of the expression shown. R is the equivalent static force. Its value can be found by expression which is obtained by multiplying the expression for finding delta by stiffness K. Once the value of R is known, the bending moment diagram and the shear force diagram can be plotted. To apply the methodology to be introduced by the following slides, the amount of reinforcement in the wall must be above the limit as shown on the table. The limit of yield and effective stiffness of the reinforced concrete wall. Once the tensile strength of the longitudinal reinforcement is known, the yield at curvature can also be found by the use of the simple expression. The bending moment capacity can be found by a standard formula as shown here. Given that we already have the curvature at yield, the effective stiffness can be found readily, and hence the displacement demand of the impact. The analytical solution that has been presented has been compared with results obtained by the pendulum testing. Altogether, 12 verification experiments have been conducted. Tensile strength of the longitudinal reinforcement. Given that we have found the value of delta, which is generated by the impact, and the value of delta at the limit of yield, we may use the principle of proportionality to find the longitudinal tensile strength of the reinforcement. Experimental verification by use of strain gauges. The maximum tensile strength of the longitudinal reinforcement as obtained using the equation presented earlier have been compared with experimental measurement on this bar chart.